Okay, so today we're going to start the light unit, and this is unit 4. We're almost done the course, just in the last little bits of it. So we will be talking about light, and we're going to review some general wave concepts. We're going to examine the evidence that light is indeed a wave. We're going to compare and contrast the particle and wave nature of light. We're going to discuss some landmark experiments with light, talk about how color and wavelength are related, and explore some current technologies. This is a little bit more of a conceptual unit, so the math is a little lighter. There are a few equations, but not many. It's also a little bit of a shorter unit. So the first thing we're going to talk about as the duality between light being a wave or a particle. So even in the ancient times, people did talk a lot about what light is. 17th century, the argument basically split between two people. We have Newton and Huygens. So basically Newton thought that light is a collection of particle, and Huygens' idea was that light is a wave. So there basically was a big discussion about these two, back and forth, back and forth. Eventually we got enough evidence to show that the wave model was actually the best model to fit our observed phenomena. So let's compare them. We're going to look in basically in terms of four different things. Rectilinear propagation, that's basically saying that light travels in a straight line. Diffraction and dispersion, where we have the scattering of light. Refraction, where light changes direction. And reflection, where we have the bouncing of light off a mirror. So let's first talk about how light travels in a straight line. Newton thought light was a particle, so he thought, well, just think of a really fast projectile. And if you move a projectile fast enough, you would think it's moving in a straight line. And that's kind of what he thought light was, really, really, really fast projectile. The wave side of that was like, well, maybe it's a flat wave front. Now, this actually, it's really hard to show that light goes in straight lines according to the wave model, because it actually doesn't. It does go slightly around corners. The problem we have with light is that the waves are so tiny with such a small wavelength that they're really not 100% the same as the water waves that were being used to study them back in the 17th century. So there are some things that water waves do that aren't as noticeable with light waves, because light waves have a much smaller wavelength. Now, it was this property that right here, this fact was really hard to explain, and that was actually a problem. And this is why Newton's particle theory probably gained so much ground, is because this whole idea of light traveling in straight lines was really hard to explain with waves. So Newton had a really good answer to this, but Huygens didn't have quite as good of an answer. There is a perfectly good explanation for it, but that depends on you understanding the wavelength of light being tiny, and at the time that wasn't well known. But reflection was a lot easier to explain. Both of them could explain this. Newton said it was a perfectly elastic collision, like imagining a steel ball bearing fired at a steel floor. A very, very elastic collision, and that's why it bounced off the mirror. The other idea with waves, same thing. Waves easily reflect off surfaces, and they do this with a angle of incidence equaling the angle of reflection. So there was really, that's kind of a tie there. Neither of them really had a better explanation for reflection. Refraction was one that I think was very interesting, because when light goes from one medium to another, like from air to water, it changes direction. Now Newton said, well, if you imagine the object speeding up, like the pellet of light speeding up, it will change direction and bend towards the normal. So if you're going from air and you hit water, the direction of the light changes. Newton said, well, imagine it like a marble going down a ramp, and if it speeds up, it's going to be closer to it's going to bend towards the center. Now with waves, that's also possible, but the wave has to slow down and it will refract. So we have basically two competing ideas here. Newton's saying, I can explain it, it just means the light has sped up. And Huygens said, I can explain it too, it just means the light has slowed down. And at the time, there was no real way to prove that. So, or at least nobody had figured out a way to prove it. So they kind of were in a dead heat at the time. However, in real life, we do know that the light does, in fact, slow down when it bends towards the normal. Light goes slower in water than it does in air. So this was actually good support of the wave model. It's just they didn't know it at the time. Now, diffraction. When light passes through a slit, the light spreads out, and when it passes through a prism, it separates into a rainbow. Now, Newton didn't really agree with the experimental evidence showing diffraction, the fact that it spreads out when it goes through a slit. He didn't think that the light could travel around corners. He said what you're seeing is the particle of light kind of hitting off the sides of the slit and bouncing off in a different direction. He could explain the separation of light through a prism. He said just have different masses. So you've got, violet light maybe being really heavy and red light being really light. So that was what he thought was the different masses of the particles made them spread out into that rainbow. But with waves, this was much easier to explain because with water waves, when they go through a tiny slit, they diffract. Light waves are really, really small, so the effect is really small. So that's why it's hard to tell. And he explained the whole idea of the separating of the rainbow is because different colors of light have different wavelengths. So red light has a very long wavelength compared to blue light, and that would give you that rainbow separation. And those are basically, I think that's as far as I kind of want to go with this one. So when we talk about these four ideas, that was really what was happening at the time. And the two really went neck and neck until an experiment by Young, which will be in the next lesson, that really kind of proved, quote unquote, the whole wave nature of light. Okay, hopefully that is helpful.